Good morning, everyone. This lecture is focused on the free space optical communications and which parameters affect its performance, or otherwise the known link budget analysis. This is within the scope of the project CYQCI, which is the Cyprus Quantum Communication Infrastructure, which is coordinated by the Cyprus University of Technology, in which I am working currently as a senior research fellow. Today we'll cover the free space optics channel models and various atmospheric losses which are encountered during the beam propagation through the atmosphere, which are including the free space path loss, the pointing loss, absorption, and scattering. This is followed by the description of atmospheric turbulence and its effects on the laser communication. Typical free space optics communication is usually considered by the optical transmitter, the amplifiers, and the receiver. The design of optical transceiver takes into account the different types of detectors, noise sources, and receiver performance in terms of the signal to noise ratio, the outage probability, fade, and link margin, which are then described. The system performance analysis, which is basically the bit error rate, is the performance of the free space optics communication link and is the ratio of errors in relation to the total number of transmitted bits. Despite of the great potential of the free space optics communication, its performance is, however, limited by the adverse effects, meaning the absorption, scattering, and turbulence of the atmospheric channel. The most challenging aspect of the free space optics communication system is acquisition, tracking, and pointing. The initial link-up time that puts a limit on the overall performance of the system, and hence this is becoming an essential system design constraint. For future techniques and improving the link performance will then be described in a different lecture, which will give the aperture averaging, the spatial diversity, the coding, adaptive optics, and any related free space optics. Finally, as a last part of this lecture will be a description in detail of the optical system designers which calculate the link budget. The free space optics communication systems are free space ACS, which acts as a communication channel between the transceivers, which are the line of sight for successful transmission of optical signals. The channel can be atmosphere, space, or vacuum, which have the characteristics determined by the transmission or reception of optical signals for designing reliable and efficient communication systems. Using the FSO technology, the data is transmitted by the propagation of light through atmospheric or space communication channels, allowing the optical connectivity. The FSO offers a high data rate to meet the tremendous increasing demand of the broadband traffic, mostly driven by the internet access and the HDTV broadcasting services. Compared to the fiber optics technology, FSO offers much more flexibility in designing the optical network architectures at very high speeds, reaching the tens and hundreds of gigabits per second rates. However, the FSO is affected heavily by the atmospheric effects, which limit the sensitivity and achievable high data rates with the acceptable bit error rate. Some of these degradation and turbulence, absorption and scattering, and various mitigation techniques do exist for reliable and efficient data transmission. Here, as we can see, there is a free space optical communication that requires a line of sight connection between the transmitter and the receiver for the propagation of the information from one point to another. When we are mentioning the ground to satellite, this is referred to as the optical uplink, and the satellite to ground is referred as the optical downlink. These involve the propagation of optical beam through the atmosphere as well as in free space. Therefore, these links are a combination of terrestrial and space links. To the left, you can see a few of the applications of the free space optics communication links as in real life, having the mobile user satellite, the user in UAVs, drones, and to the right, the point-to-point, the ring network, mesh network, which are the terrestrial links. Based on the transmission range, the wireless optical communications can be classified into 5 broad categories. These are the ultra-short range, which are the chip-to-chip communication, the short range, which are the wireless networks in personal area networks, the medium range, which are the indoor infrared or visible light communication, for inter-vehicular and vehicle-to-infrastructure communications, the long range, which are used in terrestrial communication between buildings or metro area extensions, as seen on the figure to the right, or finally for the ultra-long range, which are used in the ground-to-satellite, satellite-to-ground, or inter-satellite links for deep space missions. Now, the link budget analysis for the free space optics satellite networks is referred to the calculation of the overall performance of a communication link between 2 points using the optical signals transmitted through the atmosphere. This is further defined by the main parameters which characterize it. These are the transmitter power, which analyzes the power of the optical transmitter and is measured in watts or decibels. The transmission medium in which the free space optics transmission is the atmosphere, and it takes into account factors such as atmospheric attenuation, which is a reduction of the signal strength due to the absorption, scattering by molecules, aerosols, and other particles in the atmosphere. Then we have the path loss, which is the reduction in signal strength as the signal propagates through space. This in free space optics is primarily due to the divergence of the optical beam and atmospheric absorption. The receiver sensitivity is the minimum power level required of the receiver for proper operation. It's usually again expressed in watts or decibels. The receiver aperture or otherwise area is the size of the receiver, in which is affected on how much optical power can be captured. The signal to noise ratio is the quality of the received signal, defined as a ratio of the signal power to the noise power. In FSO, the noise sources include the background light, thermal noise, and electronic noise in the receiver. And finally, the margin is the safety margin, in which it's typically guided to the account for variations in atmospheric conditions, pointing inaccuracies, equipment, aging, and other uncertainties. A usual typical block diagram in the free space optical link is shown in this figure. And like any other technology, communication technology, it comprises of the 3 basic subsystems. This is the transmitter, the channel, and the receiver. The transmitter is primarily used to modulate the signal, the message signal onto the optical carrier, which is then propagated through the atmosphere to the receiver. The essential components of the transmitter are the modulator, the driver circuit, for the optical source to stabilize the optical radiations against temperature fluctuations, and the collimator or otherwise telescope that collimates and directs the optical radiations toward the receiver. The most widely known modulation is the intensity modulation, in which the source data is modulated on the irradiance or otherwise intensity of the optical carrier. This can be achieved by varying the driving current of the optical source directly to the message signal to be transmitted, or by using an external modulator. The channel sees it's the atmosphere in this case as a propagating medium. It's influenced by unpredictable environmental factors, which can be referred as the cloud, snow, fog, rain, or otherwise. These factors do not have fixed characteristics, and they can cause attenuation and deterioration of the signal received. The channel is one of the limiting factors in the performance of the FSO system. The receiver, which has as a primary function to recover the transmitted data from the incident optical radiation, consists of a receiver telescope, an optical filter, a photodetector, and a demodulator. The receiver telescope collects and focuses the incoming optical radiation onto the photodetector. The optical filter reduces the level of the background radiation and directs the signal of the photodetector, which converts the incident optical signal into an electrical. The main communication components of a free space optical communication is as we mentioned, the optical transmitter, the amplifiers, and the receiver. And the receiver can be then classified on the type of detectors, noise sources, receiver performance in terms of the signal to noise ratio. The transmitted power, as we have already mentioned, which emits the optical power with a varying degree of focusing, is then described by the emission angle. The total power in watts is emitted from a uniform source, which is characterized by the brightness function B, the surface area, which is called A, and the emission angle omega. This is given by the equation given here. And for symmetrical radiating sources, the solid emission angle can be related to the planar emission angle. This is further to the previous slide, which is the light that can be collected and refocused by the means of beam forming the optics as shown in this figure below. The light of the source is focused to a spot where the help of the converging lens, and diverging the lens expands to the beam, to the planar beam diameter. This is given where the operating wavelength and the transmitter lens diameter, and r is the distance of the lens of the link range. Here is a summary of the main equations which give the communication link. From here it is seen that the received signal can be increased by one or more of the following options. When increasing the transmit power, we can see that the simplest way to improve the signal is usually by increasing the transmit power, since this scales linearly with the transmitting power. However, increasing it implies that the overall system power consumption can lead to safety issues or any thermal management or so on. Furthermore, if increasing the transmit aperture, which is the size and beam width, could bring an inversely proportional to each other. Therefore, increasing the transmit aperture size can effectively reduce the transmitter beamwidth and therefore deliver the signal with more intensity. However, this may lead to tight acquisition, pointing, and trunking requirements. Further, the transmit aperture cannot be increased indefinitely, as it may increase the overall mass of the terminal and will increase the cost of the system. By increasing the receiver aperture, we have the amount of the background noise collected by the receiver, which can lead to the increase of the receiver aperture area. This implies that the effective performance improvement does not always scale linearly with the receiver aperture area. Reducing the pointing loss could be reducing the transmitter and therefore the receiving pointing loss. This would improve the overall signal power level. It could also reduce the pointing induced signal power fluctuations. To improve the overall efficiency, this is by improving the transmittance and receiving power through the appropriate optics and filter designs. The signal detection, which it's an indirect detection by a detector, has a spatial light fiber coupling detection, the distributed detection, and the coherent detection. This type of direct detection means that the optical detector directly receives the optical signal, which is collected by the antenna. In the case of the spatial light fiber coupling detection, this means that the spatial light is coupled to an optical fiber and then a signal in the optical fiber, which is detected by the photodetector. Owing to the small dimensions of the optical fiber, a small photosensitive area of the photoelectric converter, and a small optical signal intensity, it will be required. The signal can then be detected with a high rate and a sensitivity by coupling the spatial light into the optical fiber. Now, when looking into the link performance analysis of a free space optics communication, the basic components values of the system parameters are assumed to be known by and fixed in advance. For instance, we have the fixed output powder as a function of the operating wavelength, the transmitter, the receiver, the telescope sizes, which directly affect the link performance. Therefore, the link performance analysis can be performed if all components and operational parameters are precisely specified. The three basic steps for evaluating the performance of an optical link are the transmitter's beam divergence, and the receiver's aperture diameter, the receiver sensitivity, which is the minimum power of the detector which needs to receive for a given bit error rate, and the path length losses, the atmospheric attenuation, and atmospheric scintillation losses, compared to the detected signal photons and noise photons. Now, however, of the many advantages of the performance of the free space optic communication system, this is heavily influenced by the unpredictable atmospheric conditions and undoubtedly poses a great challenge to the system designers. The primary factors that deteriorate the FSO link performance are the absorption, scattering, and turbulence. Out of these, the atmospheric turbulence is the major challenge that may lead to serious degradation in the link performance and make the communication link infeasible. As you can see here, scattering is further categorized by the atmospheric turbulence and effects on the laser communication, the beam water, the beam spreading, the beam scintillation, spatial coherence, and degradation. Now, for the figure to the left, we can see the broad classification of various levels of the atmosphere, in which with the details of each layer with their temperature values, which are shown according to the wavelength that it has to be done, and therefore the wavelength has to be chosen very carefully for a high transmissive band in having the free space optic communication links. To the figure of the right, we have the atmospheric condition in which the FSO channel can be broadly classified into three categories, namely the clear weather, clouds, and rain. The clear weather conditions are characterized by the long visibility and a relatively low attenuation. Cloudy weather conditions range from mist or fog to heavy clouds and are characterized by low visibility, high humidity, and large attenuation. The rain is characterized by the presence of rain droplets of variable sizes, and it can produce severe effects depending upon the rainfall rate. Atmospheric turbulence is a major challenge that could cause degradation in the bit error rate performance of the system and make the communication link infeasible. The atmospheric condition in the FSO channel can be broadly classified into three categories. These are the clear weather, clouds, and rain, as we mentioned. And from here, in the figure here, we can see the transmitters, or otherwise known attenuation effects, as a function of the wavelength. The output in clear weather conditions is plotted for the wavelength up to 3 meters. It's clear from this figure that the peaks in the attenuation at specific wavelengths is due to the absorption by atmospheric particles, and therefore the choice of the wavelength has to be done very wisely for the high transmissive band to have communication links. To have the average particle size corresponding to the particle density in the atmosphere, this is a distribution which is shown in the figure to the right for various cloudy and rainy conditions. It's seen that in these conditions, which may vary from high density and small particle sizes, and in the case of mist and fog, to low density large particle sizes during the heavy rain. It should be noted that the figure gives the average parameters, whereas real atmospheric conditions may undergo various temporal changes. Out of the various scattering particles like the air molecules, haze, particles, fog droplets, snow, rain, and hail, the wavelength of fog particles is comparable with the wavelength of FSO communication system. This plays a major role in the attenuation of an optical signal. The atmospheric scattering not only attenuates a signal beam in the atmosphere, but it's also the primary cause for sky irradiance, which introduces noise in a daytime communication. The sky radiance is due to the scattering of solar photons along the atmospheric propagation path, and it gives rise to the unwanted background noise, which degrades the signal-to-noise ratio at the receiver. The received background noise depends upon the diameter of the receiver and relative to the location of the sun towards the receiver. The atmosphere is considered to be modeled as multiple layers, with each layer consisting of homogeneous mixture of gases and aerosols. The scattering angle is formed between the forward direction of the sun radiation and the point of observation. It is seen that the higher the concentration of the scatterers, more will be given on the sky radiance. As the angular distance between the observation direction and the sun decreases, there is an increase in sky radiance. Within 30 degrees from the sun, sky radiance is greatly dominated by the aerosol contribution. As the angular distance from the sun increases, then the dominant source of the background radiation is then given by the Rayleigh scattering. The performance of the FSO link is subject to the various environmental factors, as we have mentioned. Out of these, the atmospheric attenuation is typically dominated by the fog, which is considered as a particle size comparable to the wavelength of interest in the FSO system. It can change the characteristics of the optical signal or can completely hinder the passage of light because of the absorption, scattering, and reflection it causes. The atmospheric visibility is then a useful measure to predict the atmospheric environmental conditions. The visibility is then defined as the distance that a parallel luminous beam travels through in the atmosphere until its intensity drops by less than 2% of its original value. In order to predict the optical attenuation statistics from the visibility statistics, we have the availability of the FSO system in relation to the visibility and attenuation that has to be known. Several models were described in relation between visibility and optical attenuation are given in different work that has been published. To characterize attenuation of optical signal propagated through a medium, the term called specific attenuation is then used for the means of attenuation per unit length expressed in decibels over kilometers. These are depicted by the equations here as called beta. The attenuation coefficient, which is the sum of the absorption and scattering coefficients from aerosols and molecular constituents of the atmosphere, is then given by the equations here. The absorption is a wavelength-dependent phenomenon. The wavelength range of the FSO communication is chosen to have minimal absorption, as shown in the table here. This is referred to as atmospheric transmission windows. Within, the attenuation due to the molecular or aerosol absorption is less than 0.2 decibels per kilometer. There are several transmission windows within the range of 700 to 1600 nanometers. The attenuation can be classified into dry and wet snow attenuation. The specific attenuation, decibels per kilometer for snow rate, is then given by following equation. These values, as we can see in the two different graphs here, is the attenuation versus the visibility for heavy fog and cloud to the left, and for light fog and haze to the right. Since in the case of the wavelengths used in the FSO systems, typically 850 nanometers and 1550 nanometers, the influence of absorption is significantly minimized, and the FSO design has a high availability in a typical continental area where the rain, snow, and fog occur and cannot markedly be affected by the turbulence. The atmospheric attenuation is then predominantly affected by the MIE scattering. The atmospheric attenuation coefficient, which is the scattering proposed in one of the published papers by Kim of the meteorological visibility, is then the wavelength, the visibility, and the particle size distribution. To begin with, why it's important to have the power link margin and the link availability. The power link margin is the capability of a system to eliminate the effects due to the atmosphere particles. It depends on the number of factors, as we have mentioned. All of the other parameters is then affected by the link equation, which is the power of transmitter, receiver, the aperture area of the telescope, the elevation angle of the communication link with the satellite, and therefore the coupling loss to the receiver lens and photodiode. The PR mean is the optical receiver sensitivity. Now, to have a possible simple comparison with various free space optic systems, the power link margin is then given by the equation to the bottom. The availability is one of the most important factors when discussing the communication systems. To get a value of the availability, it is common to perform the test of the bit error rate, or otherwise BER, which is the ratio of errors in relation to the total number of transmitted bits. Within the telecom industry, it's commonly accepted that the link is considered as available until the BER equals to 10 to the minus 3, and the communication is then regarded as terminated. Other important events are the severely errored second, or otherwise ACS, which is second to the bit error rate. A period of unavailable time begins at the onset of 10 consecutive SES events. These 10 seconds are considered as part of the unavailable time. A new period of available time then could begin on the onset of 10 consecutive non-SES events. These seconds are considered to be part of the available time. A path is available if and only if both directions are available. The International Telecommunication Union requires typically 99.96% of the available time in an access or short-haul part of the network. As already mentioned, the overall system performance of a link is quantified using the link margin, and it's derived by the link equation that we have seen. The optical link equation is analogous to the link equation for any radio frequency communication link. The starting with the transmit power, the designer identifies all the link degradations and gains to determine the received signal level. The received signal level is then compared with the sensitivity of the receiver, and therefore it gives the link margin. And usually the link margin is defined as the additional signal to noise ratio, and it poses on top of the original design point to guarantee that the link can be given with a daytime criteria requirement, and is typically expressed as the bit error rate or otherwise frame error rate. In order to have the signal recovered at the receiver side, its power must be higher than the receiver sensibility or receiver threshold. The receiver threshold is usually given by the manufacturer, and it could range from the minus 20 to minus 40 decibels. A positive link margin is then required to successfully close a communication link. The link margin is simply the ratio of received power to the required power by the receiver. The required signal power is a complex function to target the bit error rate, for the implementation losses, and also for the different noise terms. Again, here we can see the different equations which are given for the power and at the receiver, calculating the link margin, which can determine the factors after the quality of the link. Here we can see that the link margin is expressed in decibels, and this is a ratio of the received power and received threshold, or the amount of power received above the minimum detectable power. If we want to further analyze on the link margin equation, there are a few terms. The equation is given at the bottom of this slide, and as you can see, it's analyzed part by part in terms. So the first term represents the transmitter factors and corresponds to the equivalent isotropic radiated power, which is commonly used in the RF systems. The second one is the medium of the beam that goes through for propagation entirely through the vacuum, except from the range losses. And the third term represents the control terms driven by the host platform stability. The last term represents the receiver's terms, which are the received power, the transmit laser power, the transmitter gain, and the transmitter losses. e.g., the optics imperfections represents the pointing losses induced by the host platform's vibrational frequencies, the range loss, the stroke loss, and the wavefront aberration stemming from the optic imperfections. Losses due to the atmospheric attenuation or due to the atmospheric scintillation. There are also the aero-optics effect, which is the boundary layer of an aeroplane's wing, or the receiver gain, represents the receiver losses stemming from optics imperfections due to the tracking errors receiver platform jitter. Moving on to the another loss, which is the free space or otherwise path loss, we can see an equal example in the light bulb analogy, which can help to understand this. The quality of the light shed over a piece of paper diminishes as we take it further away from the light bulb. This is purely a geometric phenomenon. It happens even in a vacuum where there is nothing that can absorb the electromagnetic radiation, and therefore this is why it's called free space or geometric spread loss. The equation is in the formula of base 10 log, and it's quite easy to use it as it results that for 100 decibels, as we can see from the bottom graph to the right, for 100 decibels, this is for 1 kilometer, and for 20 decibels, you multiply by the distance by 10, therefore 10 kilometers is 120 decibels, and so on. Or 100 kilometers, then you have 140 decibels. You have to remember that every time that you double the distance, it changes logarithmically. Due to the dependence of the wavelength on the wavelength, the free space path loss is incurred by an optical system which is much larger. Therefore, the factor LS is much smaller than in a usual RF system. Besides the space loss, there are additional propagation losses if the signal passes through a lossy medium, such as the planetary atmosphere. And many optical links, like deep space optical links, do not have additional space loss as they do not involve the atmosphere. This figure can show the relative amount of gains and losses, as well as the absolute power at each point in a wireless link. The transmitter provides some amount of power, a small amount in loss, in attenuation between the transmitter and the antenna. The antenna then focuses the power, providing a gain, and at this point the power is at the maximum possible value for the link. This power is called the EIRP, or equivalent isotropic radiated power, as we already mentioned. Most regulators impose a limit of the maximum allowable value in EIRP for every given country. Then there are the free space and environmental losses, which Together with the path loss, they increase with the distance between the link endpoints. The receiving antenna provides some additional gain. Then there is a small amount of loss between receiving the antenna and receiving radio. If the received amount of power at the far end is greater than the received sensitivity of the radio by a certain margin m, then the link is possible. The value m will then determine the reliability of the link, which is a good starting point to have at least 10 decibels of a margin. If you have critical links, it's better to strive for 20 decibels margin. The link budget, which basically refers to the performance of the communication and not the cost to obtain the equipment, as wrongly assumed, is then measured in the scale of decibels. To perform a link budget analysis, you could calculate the total power available at the receiver by adding the transmitted power and any gains, and then subtract the losses due to the path loss and other factors. The result should exceed the receiver sensitivity by an acceptable margin to ensure reliable communication. The link budget reflects the impact of different variables in the ultimate power that reaches the receiver, which is strongly dependent on the transmission rate higher than the transmission rate. The higher the receiver power required for acceptable performance. If one cannot obtain an acceptable margin at a given transmission rate, it might be required to work at a lower transmission rate. This is about estimating wireless link performance by using link budget calculations. Now, a lot of challenges are faced in the free space communication systems, and these are mainly, as stated already, the atmospheric turbulence, which is caused by random fluctuations, the refractive index of the air, leading to beam wandering, or scintillation, twinkling, and beam broadening. Also by the turbulence-induced effects, which degrade the quality of the optical signal, reducing the signal strength and impairing communication performance. Otherwise, we have the weather dependence, which is the FSO communication, susceptible to adverse weather conditions such as the fog, rain, snow, haze, and can attenuate and scatter the optical signal. This, for severe weather conditions, could lead to signal loss, increased bit error rates, and temporary link outages, impacting the reliability of the FSO links. In the third category, we have the limited range line of sight requirement, as FSO communication requires the unobstructed line of sight between the transmitter and receiver, limiting its range and applicability in environments with obstruction objects or terrain features. Could be an issue. The line of sight constraints pose challenges for the urban deployments where tall buildings, vegetation, geographical obstacles can obstruct the optical path. Alignment and tracking is about maintaining the precise alignment between the FSO transceivers critical for establishing and sustaining the communication links, and also factors such as the mechanical vibrations, thermal drift, and platform motion in mobile applications for satellite tracking. These are required for sophisticated tracking and pointing mechanisms to ensure continuous alignment. When moving on to the security and interference aspect, this is while the FSO communication offers an inherent security due to the nature of the optical transmission, it's yet susceptible to the interception using the optical receivers equipped with sensitivity detectors. Interference from ambient light sources, including sunlight, artificial lighting, and laser pointers, can disrupt the FSO links and compromise data and confidentiality. The regulatory considerations are the ones that the systems can operate in the optical spectrum, which is subject to the regulatory requirements and standards governing the laser safety, power limits, and spectral allocation. Compliance with regulatory requirements may impose constraints on the FSO deployment and parameters, which are to transmit power, beam divergence, spectral characteristics. The scalability and network management is limited by factors such as the number of available optical frequencies, beam divergence, and channel capacity. Efficient network management and resource allocation are essential to optimize the performance and capacity of the FSO, particularly at the multi-hop or mesh topologies. A few emerging technologies in the free space optical communications are basically the ones that hold the potential to further enhance its performance, security, and scalability in such systems, in paving the way for their widespread adoption in various applications ranging from the terrestrial to the space-based communication infrastructures. These are known as the quantum key distribution networks, which establish secure communication channels by transmitting the cryptographic keys encoded in quantum states of light. This is something that the project CYQCI is heavily dependent on at its core. Integrating the QKD with the FSO communication enhances the security by providing the unconditional security against eavesdropping. This is about having the integration of the terrestrial networks with the free space optical communication satellite-based. The second is the adaptive optics, which is systems use deformable mirrors and wavefront sensors to correct the distortions caused by the atmospheric turbulence, improving the quality and reliability of the FSO links, and by dynamically adjusting the optical path, the adaptive optics mitigate the signal degradation and extend the range of FSO communication. The multi-beam and multi-channel systems create parallel communication channels, increasing the data throughput and resilience to atmospheric disturbances. Also, they utilize different wavelengths or polarization states to transmit multiple data streams simultaneously, further enhancing the capacity and the reliability. The free space optical mesh networks are interconnected nodes equipped with the FSO transceivers, enabling the decentralized communication and dynamic routing of data. These networks offer flexibility, scalability, and resilience, making them suitable for applications such as urban broadband access and disaster recovery. There are also the hybrid FSO-RF systems, which is technologies that overcome the limitations of FSO, such as the weather-dependent performance and line-of-sight requirements. By having an intelligent switch in between these two, we have, based on the environmental conditions, the hybrid systems optimize the performance to ensure continuity or connectivity. Integrated photonics are devices that include waveguides, modulators, and detectors to enable the miniaturization and integration of the FSO components into compact and power-efficient systems. Integrated photonic facilitate the development of the chip-scale FSO transceivers suitable for applications in mobile devices, unmanned aerial vehicles, the UAVs, and the Internet of Things devices. Deep learning for atmospheric compensation is adaptively adjust the FSO transmission parameters to optimize the performance by learning the real-time atmospheric data. These algorithms enhance the resilience of the FSO links to turbulence-induced fading and improve the link availability. The space-based final communication has to do with the ground stations that offer high-speed data transmission for space-based applications such as the satellite internet, Earth observation, and inter-satellite communication, and the advances in the space-based FSO enable robust and high-capacity communication in the harsh environment of the outer space. Now, to summarize this lecture is that the link budget can be derived from a given set of system parameters and their tolerances, and is straightforward addition and subtraction of gains and losses where values are converted to decibels. Link budget accounts for an optical system. It includes gains from the antennas, telescopes, and the laser transmitter, losses in propagation through the transmitting optical path, losses through space or atmosphere, and losses to the receiving optical trains to the photodetector. The primary interest in the link budget analysis is the determination of the required power at the opposite terminal detector. These values derive from the signal-to-noise ratio or probability of bit error rate analysis, which was then considered. Any received power over and above the required power considers as the link margin. Typically, separate link budgets are required for each of the communications tracking and causation subsystems, uplink and downlink. We have also covered the emerging technologies in free space optics as future trends and the potential advancements in each of those cases. I would like to thank you for today's meeting, and if you have any questions and answers, we can answer them after this lecture. Thank you for your attention once again.